Thank you. So I want to note the change in title. The title of this lecture is called Loop Spaces and Fibrations. Basically what I've decided to do is expand. Well, I didn't get to finish last time. So I expanded the first lecture and the part about Floer theory with Lagrangian Floer theory will be postponed until tomorrow. So, okay. So the first thing I want to do is, clarifications from last time. And maybe the easiest way to clarify something is to begin by definition, which is definition of what it means to be a group-like topological monoid. Okay, so I spent, if pi 0, it's a group like if pi 0 is a group. So I spent some time last time basically trying to get around this problem of, well, if you have, in a group, if you have inverses in a topological group, if you have inverses, that's a strict notion. But if you try to do anything homotopical, it's very unlikely that you'll get strict inverses. And this basically encodes the piece of information. And so one way of stating the theorem that I stated different versions of different strength. A topological space X is homotopy equivalent to a group-like topological monoid if and only if it is it admits the structure of an A infinity space. And the next thing that I will say is I will clarify this notion of A infinity space. But before I do that, I want to say also if and only if it is homotopy equivalent to a base loop space. Okay, so this is now I can, stop giving vague things. I just didn't want, this notion seems very strange at the start until you start seeing the examples, and in particular, you start seeing that, clearly you're not going to be able to make loop spaces satisfy the property of having strict inverses. Okay? So that's the first thing I want to do. The second thing I want to do is to talk again about this A infinity space. So what I did, so again, just to recall last time, I introduced some spaces which I called Kn, which parameterize the operations between the operations of concatenation between n copies of the loop space and one copy of the loop space. Okay. So the first warning is that in Basu's talk yesterday, the second evening talk yesterday, he also talked about spaces Kn, but they are, unfortunately, they're not the same. these are not the same as the Kns from talk. Now they are related. So what I'm going to do is I'm going to stick to my notation, okay? I think it's a little bit too late to change it, but because they are related and because you now have two different things which could be called an A infinity operad, so I'll say something about operad in a second. I should be more careful about what I say by A infinity space, okay? So what I will do, so this forces us before moving on, I'm going to say they are not the same, but there is a notion of equivalence, okay? And this collection of spaces that I constructed with their operations and the collection of spaces that he alluded to with their operations, they are in some sense equivalent. So we will encounter a model for the spaces that he used. So he used this notation for what are called the stash of associahedra. He used Kn for stash of associahedra. And we will encounter a model for the associahedra, hopefully, in the last lecture. That's the warning. The next thing I want to say is what do I mean by they are equivalent in some sense. It doesn't mean actually there's a map from one to the other. It means that there is some kind of zigzag, there's something that maps to both of them. But what I do want to focus on is the fact that I describe the operations as an operation. So the other difference is that I gave operations of the form Kn circle I Km goes to Kn plus M minus 1. Okay? That's what I did. Whereas what he did, following the standard conventions, is to construct kind of much larger collection of operations, which would basically form what's called the structure maps of an operad, where he described or introduced the structure maps of operad, which goes something like this. So you go K, D, cross K, I1, cross K, ID, goes to K of the sum of ID. Okay, so one observation. So the maps that I wrote, and I will remind you in a second what they were in the specific examples that we were talking about. They, if you fix this n and you fix this m, there is still this extra label of I, okay? And this I corresponded to which subinterval are we going to take the m intervals and in which subinterval are we going to put the m intervals we started with? Here, there is no additional label. There is a unique such map for every choice of D and every choice of I1 through ID. Okay, so that's the first thing. That's somehow a difference in structure. But the main claim is that even though the things look different, they're actually the same. If you keep the associativity conditions in mind, associativity equations imply, which I haven't, I mean, I guess I wrote them down fairly explicitly. He didn't quite tell you what they were explicitly, imply that these two maps, or collections of maps, are just the ways of encoding the same data. These two collections of maps encode the same data. And I think instead of going through a proof or anything like that, what I want to do is explain what is this map. Okay? So this map here is as follows. So first, it tells me that I should take, in the concrete example that we have, a copy of my collection of intervals where I've picked actually d intervals. Okay? Okay, so there are d of these. And then this says that I should pick some I1, which is completely independent of D, but it's called I1, which contains I1 intervals. So instead of writing it as a big thing, I'm going to put it as a small thing here. And I'm going to put it right here. Okay. And then the next one, I'm supposed to pick an I2, and an I3, and an I4. And then finally, I pick a point of the space which parameterizes subdivisions of the interval into ID different intervals. And out of this data, out of this KD, which are these D choices of intervals, and these collections of let's say IJ intervals for J going from I1 to ID, should find a single interval, a single subdivision of the interval into this many, into the sum of all of these ones. This one does not enter in the sum, only these. Okay? Well, how do I do it? Well, I just stick this one here, and stick the next one here, and stick the last one here, and get my desired subdivision into the sum of all of these things. Okay? So that is the connection between what, that is somehow, how this operatic structure map arises in the context of what I was talking about last time. And if you see this, you realize that indeed these 2 points of view are equivalent. Okay? Because all I'm doing here is saying, let's not stick all of them in at once. Let's take one of them at one of them. You choose one of these, and you only do, the concatenation of intervals in one of these windows. Okay? But clearly, the operation of sticking in the intervals in all the windows is just the composition of doing one at a time for every single one of them. Okay? So from this, you can recover this map by applying the map from I1, the map for I equals 1, for the first interval, the map for the second interval, and so on and so forth. And of course, this one also contains in it this map, as long as you agree that K1, that the one thing for m equals 1 is just the identity. You don't do anything. Okay, so that was the next thing that I wanted to clarify. I think that's the last one. Yes, the last thing I want to say, the last point, is that in Basu's talk, there was a discussion of wanting to have a symmetric group action on the operand. So there are two notions of operads which are called symmetric. And this is, that is, question? Okay. So that is each space, let me just say like this. The space O of n carries a symmetric group action, and of course non-symmetric, which is just no group action. Okay. So I was using the non-symmetric situation, these lectures. And the standard thing is to use the symmetric ones. Maybe let's say this is the Morse standard. And so there are advantages to both. I mean, the theory works out better here, and there, examples are less complicated here. But maybe the honest answer is that this theory of symmetric operads is necessary when you start thinking about commutativity. And we are not going to be thinking about commutativity here. So therefore, we don't need it. That's essentially why I didn't introduce it. Needed to think about commutativity. Okay, so with this in mind, you can hopefully put the content of the all the lectures together and not be too confused. Okay. So, sorry. There's one last thing I want to say. So because we have two different models for this what is supposed to be equivalent operads, it's going to be maybe better. So let me just see how I can say this. So we can define a notion of A infinity operad to be any operad which is quasi-equivalent, which is equivalent to the associative operad. Okay, so now I have this language of operads. I guess I might as well just use it. So what is the associative operad? The associative operad, so again, slight variance from what Basu did. The associative operad, which has A of n equals point for all n greater than or equal to 2. Okay. What does equivalent mean? It means there, you have your operad O, and there is a map from O of n to A of n. Okay. So this map respects the operatic structure map, compositions, and is a homotropic equivalence. If you think about these spaces of intervals, they're always contractible, and the point is contractible, and the projection is clearly going to respect composition. So really what this means, O of n is contractible. if you fix one of these, so if you don't fix one of these things, sorry, let's say it differently. If you fix one of these things, you fix one of these operads, if you fix an A infinity operad, let's give it a name that we haven't used before, O, okay? Then we say that a space X is O algebra if, well, just like last time, if there are maps O of n cross x n to x, okay, satisfying the appropriate associativity properties. So what I really explained last time is that the base loop space is a K algebra, where K is this collection of spaces here, corresponding to subdivisions of the interval. Now, sometimes you don't want to specify the actual operad, and you just say X is an A infinity space if it admits a structure of an O algebra for some A infinity opera. Okay? So that's at least one way to clarify the situation with, is you should want to think of this choice of K that we're making here as some specific model for a general notion, which is the notion of this A infinity opera. Another model would be to take A to be just to be just the associative operad, and then you basically get topological monoids. Oops. Okay. So now what I want to do is I want to just explain, yeah. O is a K algebra. Yes, what do I mean by that? So K was this collection of spaces which are the partitions of the interval into subintervals. Okay. So I just want to kind of give the idea of the proof of this kind of result that I just mentioned again at the beginning of, maybe you could call it the recognition principle of the de-looping theorem, or whatever you want to call it. Okay. And the idea is exactly the same as the proof that if you are given a topological group, then there is a space, then it has a classifying space. So construct a classifying space for each associated to each A infinity space by a two-sided bar construction. Okay. Now, if you do a two-sided bar construction, that, as I explained it last time, there was no operad. So what you do actually is you can do a two-sided bar construction which involves the operads with respect to the operad acting on the space. So I think, given the time, I'm not. I wanted to explain this, but I'm not, because we're not quite going to get there. But I do want to explain what happens for this one, where there's a smaller model. So if the operad is sufficiently nice, okay, and the technical word here is something like cofibrant, but let's not say it. Then there is a smaller model. Then this huge, this two-sided bar construction, roughly speaking, you first do a bar construction on the operad and then you apply it to the space. So it's really it's like twice as large as the usual bar construction, which is already quite large. So you can get away with something which is much smaller. And what you do is the following thing. And so I will use K, because K does satisfy this. E.g. K. You can instead apply. You can consider the disjoint union of x to the n crossed with k n plus 2, modulo an equivalence relation. Okay, so this should look kind of familiar, because when I explained the bar construction, we again had that, like, the n cells were like x to the n times delta n. And what you can do basically in this case, when the operad is very nice, you can get rid of the simplicial part and replace it by the operad direction. And that's roughly speaking what we're doing. So what is this equivalence relation? This equivalence relation is just saying the following thing. So if I take x to the n cross kn1 cross kn2, where n1 plus n2 is equal to n plus 3, then there are two maps that you can define, and a choice of I, and I, well, let me just, between 1 and n2. So there are two things you could do. You can either map this to x to the n cross kn, okay, by kn plus 2, by composition in the ith variable, or you can apply kn1 to eat up the first collection of you can apply kn1 to n1 of these factors. To x to the n1. Okay, and this will then land you in x to the n2. Okay, so now there is some numerology to be done. I claim it goes to here, n2 minus 2, k to the n. Okay, so that's the equivalence relation that you do. So this construction, so you may be wondering, why is there this n plus 2? Okay, and here. Yes. Yes. So you may be wondering why there's that n2 plus there. Well, it's because secretly, just like in the bar construction, so the reason that there is this 2 is that this is an instance of a construction which takes as inputs spaces P and Q with actions of X. Okay? Actions of X. And then in general, you would be doing P cross X to the N cross Q cross K N plus 2, and then you understand why there is an N plus 2 there. Okay. So that's anyway, so that's the point here, and this is just a special case where P equals Q equals a point. But in particular, if you set, I'm going a little bit fast because this is very analogous to this two-sided bar construction. If you set P equals X and Q equals a point, you get the analog of the So this thing here, this quotient is roughly speaking Bx. Okay? But if you do this, you get the analog of Ex. Okay? Because there's basically this extra X factor, and if you project off this X factor, and this is contractible. And again, this construction really only works because it turns out that the KNs are themselves contractible. So I'm using a lot of special properties of this operator. And so when you do this, you get this fibration sequence, just like in the case of groups. But there's always a different fibration sequence, P, Bx, loop, Bx. Okay. And then you use the fact that both of these are contractible to construct a map like this. And so these are both contractible, and this is homotopy equivalence, so this space is the same, so this is a homotopy equivalence. And that's what you were looking for. Okay? So that's very quickly how this construction is proved, and if you want to go through the details and really understand what's happening, the best thing to do is to not try to use this trick here where I kind of tried to simplify the construction, but really think about what this two-sided operatic bar construction would be, because that will give you a stronger theorem, and this will only give you a theorem for, if your X has an action by this very special operator, whereas you want something more general. Okay, so that was the sketch of that proof, and so this one, this is the path space. This was the the based path space. So Bx has a base point, and if you look at just paths, Bx, this is Bx. Okay? So, the main example, I went through this story to just merely motivate and describe a little bit what how A-infinity algebra show up in topology. But the main examples that we're going to think about, and it looks like this will only be tomorrow. So if L inside of M, so if this is a Lagrangian submanifold, of a symplectic manifold, then I want to think about the loop space of L. That's exactly this construction we were talking about. And I also want to think about this space. Okay, so let me explain this notation. So I said M Lagrangian, M symplectic, but this has nothing to do with M being Lagrangian and M being symplectic. It's just something for topological spaces. So let me use a slightly different notation to kind of highlight that fact. So if X comma A is a pair of topological spaces, and for now I'm going to say based topological spaces, i.e. you have a base point, it's an element of A, and A is a subset of X. Okay. And what do I mean by this omega 2? Well, there's a 2 here, so there's actually such a notion for every I, but I really want to focus on that one. But let's do the previous one. So we set, then I want to define omega 1 of XA to be the set of paths gamma from 0, 1 to X, such that gamma of 0 equals the base point, and gamma of 1 is an element of A. Okay. So the picture is that here's the ambience, this whole blackboard is X. This is A, it's a small petrifis, this is the base point, and we're going to look at paths that start at the base point, which happens to be on A, move in the space X, and end back on A. Okay, so 1 here is just this guy. So now we switch 1 to 2. What is this? This is going to be the space of maps. You don't want to use gamma. Gamma usually for me is always a curve. Let's just call it U. From the disk, to disk, to X, mapping S1, sorry, U of 1 is equal to the base point, and U of S1 is contained in A. Okay. So the picture, here's the base point. Here's A. Here's my U of the 2 disk. 1 is the 2 disk is this 2 disk. And 1 is this point 1 on the 2 disk. Okay? This is the unit 2 disk. Okay. So I claim that that this is also an A-infinity space. So if you go through an algebraic topology book, it will actually prove for you that this is a loop, this is an A-infinity space. It will prove it by proving that this is actually the base loop space of something. But I don't want to do that. If you do it like that, then you don't see the disks. You just see loops of loops, and I find that very confusing. Actually, you see loops of these paths. That's not, I mean, it's correct, but it's not helpful. So what you can do instead is you can explicitly make this into an algebra over this K operad. Okay? Now, as with many things, to make it an algebra over this operad, you have to take this disk and draw it slightly differently, and take these conditions and draw them slightly differently. So to do this, oops. We recast, and this is going to be a homeomorphic space, so we're not going to change anything. Omega 2 of xa as this space of maps. So here it was a 2-disk, and now instead of a 2-disk, I want a square. Okay, it's the same thing, it's homeomorphic, nothing changed, but I want a square. And not only, sorry. This space has a space of maps from square to x with the following boundary conditions. So I'm going to draw them instead of writing them because it's just. So I'm going to draw a square. Okay, and the inside will go to x. Okay, and now this interval will map to A, and everything else will map to the base point. Okay? This one maps to A, and everything maps to the base point. So now, how is this an algebra over the operand? Well, if I take two of these things, I can just stack them side by side and expand this so that they have the same length. Okay? So, given, maybe the easiest thing is I'll just do two of them. Given pair U1, U2 of such maps, and an element of K2. Well, what's an element of K2? An element of K2 is just the subdivision of the interval into two intervals. So let me just draw that. Something like this. So what am I going to do? I'm going to take the first one, and I'm going to put it here. And I'm going to take the second one, and I'm going to put it here. Okay. So if you look at this, this doesn't look like a square. But you can just fill it in, because this goes to the base point, this goes to the base point, this goes to the base point. You just fill in everything else by the constant map to the base point. Okay? If you don't like this, and you're completely entitled not to like this, you can do the same method, the same Moore method that turned the loop space into an actual monoid. You can do the exact same method here. Instead of talking about squares, you talk about rectangles, and the rectangles are going to have different sizes, and then when you stick them together, you can just get what you want. So, anyway, so alternative, use Moore method to allow different sizes. So this is the explicit combinatorial way of doing it. But for symplectic topology, it's really useful to keep thinking about this guy. Okay? Because that's somehow what's most natural from our point of view. Okay. So these are the spaces we care about. The loop space of a topological space and the and this second loop space, some kind of relative loop space of the inclusion of a space inside another. Now the next thing I want to do, and actually my goal in this remainder of this lecture and in the next lecture, is to try to develop some methods for understanding the homology or the homotopy type of these spaces using Morse theory. Okay, but using Morse theory is a very different nature than what you might have seen elsewhere. So we want to use goal, use Morse theory on the base on A in this case to describe the homology / stable homotopy type of this loop space, of loop A and loop 2 XA. Okay, and this will basically take this lecture and the next one if everything goes according to plan. So we will see this at the end of the next lecture. So, in order to get there, the first thing we need to do is we need to understand more carefully the relationship between the topology of A and the topology of its loop space. And we have this path fibration, but it's not, well, we will use it, but I want something else. I want something that more carefully, better recovers the algebraic structure. So, for the rest of this lecture, we will try to use the path fibration. It's really hard for me to write loop A, so I'm going to go back to writing loop X, the path fibration. Px X loop X. Okay, so clearly this path fibration tells us a lot about the topology of loop X. But what I want to do is to understand loop X together with its product. Okay, so that's the thing that's usually missing from this picture. If this is all you have, it's not clear how you recover information about loop X. So let me explain how this is done. So let's consider the following general situation. I have E1 and E2. They're both fibrations over X. I can define a topological space of maps between E1 and E2, which are maps over X. of maps of topological spaces E1 to E2, which make the diagram commutative. Basically, you have a map, f of E1 projected to x is equal to the projection of E1. That's just what it means. Well, this means you have a category. So you have a category of such spaces. And I claim that there is a canonical object in this category, which is the path space. Now, so the main claim that I want to make is following theorem. No, unfortunately, I don't know a good reference for this theorem, so I will try to prove it. Oh, sorry, yeah. There is a natural homotopy equivalence from the loop space of X to a space of maps over X from the path space to the path space. Okay. So this So the map the way I wrote it is actually very easy to write down. So let me explain. So the map just takes the following thing. What does this mean? This means, roughly speaking, for every point in X, for every point X in X, I should have some assignment that takes a path from the base point to this point to another path from the base point to this point. That's what it means. And this assignment should vary continuously as this second point here is moving around. So that's the right-hand side. Well, the simplest way of taking a path from X to the base point and assigning to it another path is to concatenate with a loop. Okay, that's clearly a rule that is universal for all X and takes a path from the base point to X to another path from the base point to X. So that's the assertion. The assertion is that this map, so this space is again really huge, much bigger than this loop space, but that this map is a homotopy equivalence. So what do we need to do? We need to find the map backwards. Okay. Well, it's obvious that there's a map backwards. The map backwards says, well, this is a fiber-wise map. In particular, it gives me some map from the fiber over the base point to the fiber over the base point. Okay. in the fiber over the base point, I have the constant map. Okay? And therefore, I see where the constant map goes. Well, the homotopy inverse. Which basically says if you have a map phi, it goes to phi of the base point. Phi at the base point of the base point. Okay, so we have a map. We have maps in both directions. It is easy to see that if you go from here to here and then back to the loop space of X, it's the identity. And so the main problem is to understand why is the composition the other way homotopic to the identity. And the image of the composition. So the reason that I don't know any reference for this result is that usually this result is proved by, some kind of spectrum. I mean, essentially, people don't usually prove that this is homotopy equivalence. They usually prove something much weaker, that it's a weak homotopy equivalence. How do they prove it? Well, they take these maps and they analyze them and they show that they induce isomorphisms on homotopy groups, and then by some kind of spectral sequence on X, on homology, by some kind of spectral sequence on X, and then they're done. Okay, but I think it's actually important to know what these equivalences are in order to be able to generalize them. So let me observe something. So what I want to observe is that, this homotopy, we're going to build it from two steps. Okay? So there is a natural map from this space, map over X from Px to Px to the maps not over X anymore, from Px to the loop space of X. So what is this map? This map does the following thing. So I have an element in here. Let's call it phi. Okay. And then, so let me do the thing that the algebraic topologist would do. So by junction, this is the same as a map from Px cross map over X, Px to Px to omega X. Okay? I've just taken this maps and I pushed it to the other side. Okay, so now, let's say that I have a path here, let's call it gamma, and let's say that I have an element of this map space here. And what I do is I assign to this the result of concatenating gamma with the inverse of phi of gamma. Okay? Where here the inverse is in the sense of loops. So the picture is like this. base point, some path gamma, okay? Now this path gamma, if you apply phi to it, you get something called phi of gamma, which has the same endpoint. This phi gamma inverse says, well, instead of thinking about it as a path from here to here, think about it as a path in the other direction. And the concatenation is the loop that you get. Okay. So this form is the form that is clearest geometrically, but this form is the one that I want to use. So now, sorry, can you just repeat that? They have the same endpoint. And the reason they have the same endpoint is because this phi is a map over X. What does it mean to be a map over X? It means it preserves the projection, and the projection is the map to the first endpoint. So now there's there's two steps, two remaining steps. Step one, let me give a name to this. Rho. So the first step is to show that the identity on map over X, Px is homotropic to the map which sends gamma to gamma concatenated at 0 with rho of gamma. Okay? This is some kind of tautology. It's a little bit confusing what I'm exactly doing. So, because everything is taking place just over this one. Okay? So, this concatenation at 0 is what I used here. Here I used it for a base loop that was constant, not varying with the path. Now I'm saying, now we have some recipe of assigning a base loop to any path. Okay? So if you're given a path, what you do is you concatenate this, not with something constant here, but with this one. Okay? Actually, inverse. So this homotopy, so if you look at this picture, what does this look like? So this looks like this. Here's the base point, here's gamma. Then you do this phi of gamma, inverse, I'm not going to do inverse. And then you do gamma again. Okay? And if you think exactly about what I did with this inverting thing, you're running over gamma once, and then you're running over its inverse once. And so this is just a matter of undoing this homotopy. Is homotopic. So the homotopy is just homotopy where you go along a path, and then you come back, and then you start doing that for less and less and less time until you're constant, except that you only do this part in the part where you're doing gamma and gamma inverse, and you still have this part where you have phi of gamma. So after you've done that homotopy, you exactly have the map that you started with. Yes? So that's what, yeah, that's what rho is, but I used rho inverse. That's right. So rho is you go forward gamma, and then you go gamma, and then you go phi gamma inverse. That's right. But then over there, you invert that. So you do gamma, gamma inverse, and then this one inverted once. Okay, so that's step one. And step two is, we just have to analyze this map rho. That's all we have to do. Okay. Two, the map rho is homotropic to the map. Well, let me just write it. So I have maps over X px, okay, going to loop X by what we said before, phi of the base point, okay? And this goes into maps from px to loop X by just the constant map. So this construction is kind of a slightly complicated construction because, again, the loop that you concatenate with depends on the path that you take. Okay, that's what's going on here. Loop that you concatenate depends on the path that you take. Whereas the map that we really want, when we want to show this equivalence, is you have a fixed loop and you concatenate with that fixed loop. And what this is saying is that those two things are homotropic. Okay. What's the proof? So to prove this, you don't have to do anything. Just draw a picture. So this rho map is like this. Phi of gamma, gamma. Okay. Now think about what happens when you take this gamma and you retract it. Okay. Well, as you retract it, you get some other something which may be called, maybe it's better if I use colors. Gamma, phi of gamma t. I'll use another color for another one. You retract it further. And you get some other loop. Maybe travels a lot. This is gamma t. This is phi of gamma s maybe. And you keep going until you reach the gamma of 0, which is this constant map. But this constant map is exactly what we started with. So when s equals 0, you just have a loop. Phi. Okay. So it's this the usual argument when you're trying to use path spaces and their contractibility, you just run the path backwards through time. Okay, so you just look at this diagram. Retract gamma to the base point. Okay, so that's the proof of this theorem, which, as I said, I don't know where it's written. Its proof is very basic, so I suspect that somehow this is something that was definitely known in the 60s and 50s and 60s, but I don't know if it ever made it to print. Now, this story with loop X actually has a generalization which is important to know. More generally, we obtain an equivalence between modules over loop X and fibrations over X. What do I mean by an equivalence? I mean each of these is a category. So I haven't where each of these is a category. Okay. So modules means spaces together with an action of loop X. What does that mean? Well, if your favorite thing, turn loop X into a monoid, since we know how to do that, and just take action of that monoid. Spaces with loop X action. Okay. And the other one is this map X. Use map X E1, E2. And what do I mean we get an equivalence? Okay. It doesn't mean that these categories are isomorphic. That's not true. That's very unreasonable for the kind of setting we're in. What it means is there is a functor that induces a homotopy equivalence. Let's just all spaces have the homotopy type of CW complexes, so we can just say that. So homotopy equivalence on morphisms. And roughly speaking, here it's clear what I mean, and here it is not completely clear what I mean, because you really have to be careful with how you define maps between such spaces. So you need a careful definition of maps of omega X modules. Okay? So that's where we stand. So the next thing, there's now two things to be done. One thing to do is to explain. So far I've managed to, we will talk about spectra at some point, but I managed to not talk about spectra at all. What I've done is, the way I think about it is, this is the nonlinear part of the story. This is the theory part about spaces. At some point, we're going to linearize, whether that means passing to homology or whether it means passing to spectra. That's what we're going to do. But first, we should understand everything that can be understood before linearizing, and this is the kind of data that we will need. Okay. That's the first thing. The second thing that we will need to do is do something analogous for this kind of space of based disks. Okay. And so this requires some more topology, so let me explain. So next, we do something similar. For loop 2, I'm going to do XA. Okay? So now loop 2XA, there are many ways of trying to think about it, but from my point of view, it's very important to try to do everything over A. Okay? Because eventually what's going to happen is that X is going to be this symplectic manifold, L is going to be this Lagrangian, A is going to be this Lagrangian, and I really want to do something finite dimensional. So if you ask a homotopy theorist, they would say, again, they would tell you loop 2 of XA, that's just loops of this loop 1 XA, so just treat loop 1 XA as your X in this story, and then you're done. Okay? But I don't want that. The loop XA is too big. It's not something I can get my hands on. Okay, so over A. Good. Sorry. Just before I move on, this map is compatible with compositions. Okay? That's something important that we will need later. Okay? Here there's a product, here there's a composition, and the two things are compatible. And I want something similar here. So the starting point is the map from that I introduced earlier from, no, not quite, from the path space of A to loop 1 of x. Okay, so just to make sure we understand what's happening, here's the base point. Paths means things which live here. These are things which go outside. Okay? And so paths on A, loop 1, XA. Okay? So clearly we have such a map. Good. So what I want to do is I want to fix, so for each point x, we get space of paths from x to a, including inside these loops, loops x, a, which evaluate down to x, but this is the same thing as paths along x, paths along big X with endpoint on x. Oof, too many x's. So all I'm trying to say is that this guy has an evaluation to a, okay? But if you take a fiber over some x here, okay, the fiber over that x is exactly the same as the space of paths in the bigger space. So this inclusion, if I really try to think about it one point here at a time, it's just this family of inclusions. So what I want to do so the analog of the theorem that I'm stating, that I'm erasing, that there is a natural equivalence between the second loop space, the relative loop space, and something which I will describe as follows. So, sorry for the notation. So first I want to write gamma A, and here I want to write maps over px of PA, okay? And finally, I want to put some quotation marks. No, I want to put them in red. I want to put quotation marks here. Okay. What does that mean? So this is not loops. This is paths on X from the base point to A. So there is a base point, which is fixed, and it lies on A. Okay? So here you say you look at paths which go through all of X, and then at the other point end up on A. Here you look at paths which remain on A for all time. They're just inclusion. Yes, once you do this, it's the same point. So let me just, there you go. It's the same point. Originally I was saying this space, yes. Once we're talking about these fibers, it's the same point for these fibers. Okay? So now I want to explain what this notation means. So gamma A just means the space of sections. Okay? That's all that means. So therefore, the key thing is, what is this map? Well, map over P X. Space of sections. So Space projections of which fibration? So for each x in A, we have a space. And now I'm going to put again, between quotes, map over P, over this guy, x from P x A to P x A. It's the same as before in some sense. So this is a space, okay? I don't want to consider arbitrary automorphisms of this, which is what I was doing before. I want to take arbitrary automorphisms which preserve the projection, okay? Self-maps of the space of paths with endpoints, just like before, endpoints on x and the base point, self-maps of the space of paths, which preserve the projection to the space of paths in X. Okay, and so now the problem is exactly, these quotation marks are about this statement here. What do I mean, the projection? This is an inclusion. Okay? The paths which lie on A include in the paths which go through the whole space. So if you define this just naively without the quotation marks, there's nothing, there's only the identity, because if you preserve the projection to this, then you're not allowed to move at all. Okay? So what the quotation marks mean is that you need to replace this map by a fibration. Unfortunately, there is a canonical way to do it. The quotation marks mean replace PXA by a fibration over PXX. Okay. What's this fibration? Actually, it's not so bad. It's just the space. This is the space of, well, let me draw a picture. Okay. So it's a space of disks, maybe bigons, where one endpoint, so it maps like this. So this goes to A, and everything else goes to X. So this space, I don't actually want to give it a name. I want to call this space quotations, PXA in quotations. Okay? It obviously has a map to PXA, which is just you restrict to this end. Okay? And this map is a homotropic equivalence. Okay. On the other hand, it has a map to PXX, which is to restrict to the other end. Okay. And that map is a fibration. So, yes. So that's the definition. So another way to do this, so the correct definition is instead of putting the quotation marks here, you just take these spaces and you replace them and you put the quotation marks there. Okay? But what's going to happen is I'm going to get sloppy and I'm going to stop putting quotation marks. So the proof of this theorem, and which I'm not going to give, is exactly the same as the proof of the corresponding theorem for the loop space. You just have to keep track of these evaluation maps. So I'll just write that. keeping track of the map between paths on A and paths on X. The proof is the same as before. Okay. So what we have, so it's not clear that, well, I don't know exactly. I'm not sure you want to think that we've gained or lost anything, but what I want to say is that from my point of view, what we have gained is that this has some algebra structure, some composition. It's described by some very complicated, well, by some infinite dimensional procedure, which is you work in this space of all maps and you concatenate maps. Here, you're working over a base, and then your composition is just some kind of stupid composition. You just compose maps. Okay? So we've traded the complexity of the topology of composition here for some very easy composition that's almost tautological. Okay? And then some maybe complicated topology of taking space of sections of something. So that's what's gained. So what I will do this afternoon is I will explain what it means to linearize this story. So to linearize the story, naively means passing to homology, but instead I will describe everything in the language of spectra. And then, if I have time, I will use that picture to then try to do Morse theory in this framework. So, next lecture, spectra, and then some Morse theory. Okay, yes? Nothing about Lagrangians. There won't be anything. So when I do Morse theory, we will start assuming that X and A are manifolds. We don't even need the X to be manifold, just A to be manifold. But it won't be until tomorrow that we'll see any Lagrangian. Okay? Yes? Yeah. So this, if you just say it in terms of, if you ignore the fact that I'm talking about categories, if you just talk about the object, so this is something classical. So if you have a fibration, then one of the definitions of a fibration is that you have some kind of parallel transport maps, and then you can. So one way is if you have E over X, and you have a base point, and that's the fiber, okay? Then loop X acts on F, okay? Exactly, by some kind of generalized monodromy. Okay, so the way it's usually done in algebraic topology textbooks is you say, there's some kind of path lifting property, and then you just kind of use the path lifting property for this is some kind of universal object for which the path lifting property applies, and when you apply it to it, you see that, it will take the fiber and it will bring the fiber back to itself via some homotopy automorphism. Okay, so that's the map in one direction. The map in the other direction is actually the bar construction. So in the other direction, it's pretty hard to do explicitly. What you do is you replace X by the bar complex on the loop space of X. Okay? And you want to construct a fibration. So clearly constructing a fibration over X and over this thing are the same. So what you do is that now if you have a module over loop X, you have this bar construction, this two-sided bar construction, you apply it and you get a fibration over bar loop X. So I won't write it down. So that's what you do.
Are there any further questions?